using a matrix method, solve the simultaneous equations. Now what we have there is the pair of simultaneous equations already written in matrix form. We have the matrix equation. We may proceed to solve it. In solving the equation, we will make the column matrix of unknowns the subject of the formula, which requires that we eliminate the matrix of coefficients from the left-hand side. In solving the equation, this matrix of unknown will be the subject of the formula. In order to make it the subject of the formula, then this matrix will have to be eliminated from the left-hand side. We will eliminate this matrix by multiplying by its inverse. And there we have the template of its inverse. Of course, you notice that there is no value inside there. It's just a template, an empty template, with the exception that we are labeling the positions of interest. Now here we'll have the determinant. So we will have 1 over the determinant, and that we will multiply by the adjoint. That is the determinant of this matrix and also the adjoint of this matrix. The determinant is the product of the leading diagonal minus the product of the subordinate diagonal. There we have the leading diagonal. Our intention is to have the product of the leading diagonal minus the product of the subordinate diagonal. So we'll have 2 times 1. Well, I was just looking for that subtraction sign. There it is. Minus 3 times negative 5. That is the subordinate diagonal, and we will, of course, subtract the product of that subordinate diagonal. The product will be 3 times negative 5. Now we have 1 over the determinant. We can remove this label here saying that the determinant should go there. So we will eliminate that label and we'll take a look at the adjoint. How do we form the adjoint? The adjoint, well, notice that we are beginning with the matrix itself. The matrix is written without any change, and then we will make the change on the spot. The adjoint is formed by exchanging places of the elements of the leading diagonal and changing the signs of the elements in the subordinate diagonal. We will exchange the places of these two, and we will change the signs of these two. Now, this will be changed to positive. In order to change this to positive, all that we need to do is remove that negative sign. Because if there is no sign there, we know that the number is positive. Positive is the default sign. And we may just place it at 3 because the 3 will be changed to negative. Now, this is by no means a method or routine when we are handling the adjoint of matrices. This is just done conveniently in this particular case because this number was negative. To change it to positive, we can just remove the sign, and of course this one is to be changed to negative because it is positive at the moment, and all that we do is just place the sign there. So when we are manipulating matrices in terms of finding their adjoints, that is by no means what we call a consistent or a reliable method. It is just because it is convenient in this particular case to do so. There goes your adjoint. Balance the equation by multiplying by the inverse matrix on the right hand side also. This equation will be balanced by multiplying by the inverse on the right hand side. This is the entire inverse. We expect that we are going to multiply by the adjoint on this side, and no doubt later on we will have what we know as the simplification of this arithmetic expression right there. Notice what is taking place here. What is the significance of giving space in order that this matrix will be placed to the left of this one? Why not just place it right here? Because we are just multiplying. Why not just place this matrix here? Well, there are two reasons for it. One has to do with the order of the matrices in a product and the order of the answer. And the other one is because matrix multiplication is not commutative. Therefore, the order in which we multiply matrices will affect the results. Now, we have the inverse here, which is to the left of what we are multiplying it by. Therefore, on the other side of the equation, it has to be placed on the left-hand side also. So when we put it on this side, it has to be to the left of whatever we are multiplying it by. Because it is to the left of what we are multiplying it by on the left-hand side, it has to be to the left of what we are multiplying it by on the right-hand side. Because matrix multiplication is not commutative. Simplify the determinant. We have the determinant here. We are going to simplify it. 2 times 1, that's 2. Notice that negative times negative is positive. Therefore, we will have 2 plus 15, and that will turn out to be 17. Therefore, we have 1 over 17 times all of this. There we have our first step in the solution of the equation, which is to multiply both sides by the inverse of the matrix of coefficients. We have on this slide the equation of the last step that was on the previous slide, so there is no obscure section in this process. Remember that we are multiplying by the inverse of the matrix of coefficients, the inverse of this matrix, in order to eliminate it from the left-hand side. How is the matrix eliminated from the left-hand side? Here we have a particular matrix and its inverse. When we multiply a matrix by its inverse, we get the identity matrix. A matrix times its inverse is equal to the identity matrix, which is 1, 0, 0, 1. The product of any matrix and the identity results in the same matrix. The product of a matrix and the identity. Multiplying the identity by the matrix of unknown, all that we will get is the matrix of unknowns. And notice that the right-hand side has been consistently the same throughout the entire process. What we are doing here is eliminating the matrix of coefficients from the left-hand side, and that we have done successfully. When we find the product of the right-hand side, the equation will be solved, but the answer will not be in the correct form. We will go ahead and find the product of the right hand side. That we will do on the next slide. Again, there is no obscure section in the process, because whatever we had incompleted on the previous slide is carried over exactly to this slide. We will begin with the first row of the first matrix. We said that before. We are just finding the product of the right hand side. Notice that what we have here is exactly the product of the right hand side, and we will begin with the first row of the first matrix, and we have only a single column. There is only one column which will be multiplied by each row in turn. Row by column, and you will see that the first will multiply the first, the second will multiply the second. 1 multiplied by 5 plus negative 3 times 13. We are finished with the first row. We move to the second row. The second row will now multiply the single column that we have there. 5 will go with 5, and you imagine that 2 will go with 13, meaning that the first goes with the first and the second goes with the second. What we have here is a simplification of the arithmetic that we just carried out. We have 1 5 is 5, and negative 3 times 13 is negative 39. Also 5 5 is 25, and 2 times 13, 26. What do we imagine? A simplified version of these will be placed in the result there. 5 minus 39, that will give you negative 34. 25 plus 26, that will give you 51. Remember that the result is the right hand side. The left hand side is the matrix of unknowns, and I'm going to try to digest this myself before explaining it to you. The right hand side, which is what we have here, which is this, is the right hand side of the equation. The left hand side is the matrix of unknown. Therefore, xy will be this result. Whatever we have here, that will be equal to the matrix of unknowns. And it is taken here, copied down exactly, with the exception that we understand that the left hand side should be the matrix of unknowns. We will go straight ahead to find the value of x, which will be demonstrated very clearly with these animations. What will be the value of x? Negative 34 divided by 17. And the value of y, as you imagine, will be 51 divided by 17. Negative 34 divided by 17 is going to be negative 2, and 51 divided by 17 will be 3. When solving simultaneous equations by using a matrix method, the matrices should be a part of the method and not the presentation of the answer. If we are solving a pair of simultaneous equations, your answer should not be in matrix form. You're not really solving a matrix equation. You're really solving a pair of simultaneous equations, which will give you a value of x and a value of y. Therefore, when you are presenting your answer should not remain in a matrix form like this, but should be written ordinarily as x is equal to negative 2 and y is equal to 3. Teachers and instructors, get unlimited access to teaching aids for your virtual classrooms at richardjamesmathematicsresources.com. Also, this is the best place for the hearing impaired to master mathematics as long as you are literate.